So in this part, what we're going to do, we're going to talk about adding exponents to our number parsing, to our floating point number parsing problem. We can have two different kinds of floating point numbers, really. We have the basic one, which is just really an integer because it doesn't have a floating point. Or we can have one that has a floating point number in it, or with a decimal point. There are two possible scenarios. One, where we have a floating point here at the end like this with the exponent, just like so, and one where we have the exponent here. In either case, it doesn't matter which one you do, you notice that the exponent is always the last part that we're going to be looking at. That means there's nothing that's going to come after it when we're reading the string. And additionally, the exponent part is always an integer. This part is an integer, this part is an integer. And that's going to inform how we're going to solve this problem. Notice that in the existing solution, we already have a power variable. And this power variable is just where is the decimal point. Now, once we part the e part, either let's say we have an e -3 or we have an e4, we need to decide how we're going to do this. Whatever the power value is, if let's say it's e -3, it means that power, we're going to have to divide it by 10, or we're going to do this 3 times. Because each time we do that, we're moving the decimal point to the left. On the other hand, in this instance, when we have it, we're going to take the power, we're going to multiply it by 10. And we're going to do that 4 times. And each time we do that, we're going to move the decimal point to the right. Making this observation means that we'll be able to significantly simplify the logic we currently have for parsing the numbers, or not simplify, just clean it up a little bit to make it more readable. And then we'll be able to write the logic for actually adding support for exponents. If we take a look at the original implementation over here of A2F, this is coming directly from the text, so you should be able to see it yourself. This is presented here for sake of completeness so you can see what's going on. The logic here is fairly straightforward. And if you look at the end, what we're returning is the sign multiplied by the value, so we get the right sign for the value that we've computed by parsing the string. And then we divide by the power, which we did above here earlier when we computed the number of digits that we did before that. When we're doing the calculation with the exponent, we're going to do a few small changes that are going to simplify our final logic, but besides simplifying, actually going to help us solve the exponent problem as well. So observation number 1 is we are going to set the power to 1. Having this default value is helpful because dividing or multiplying by 1 at the end doesn't change anything. So if we never have an exponent or we never have any changes, it isn't going to do anything. It's just going to keep the value as is. Then we're going to have an exponent part if 1 exists, and an exponent sign, and we'll default that to 1 as well. Same kind of logic. I'm going to walk over the parse int at index in a little bit, but this is a new function that we've added because we know that we just have the exponent part that we may have to deal with. And so now the logic continues. We do everything standard up until the first possible encounter of either the exponent part, the e, small e, or the capital E. This is an instance whereby the exponent occurs before the decimal point. What we then do is we parse the rest of the string and treat it as an integer from the next index position, and we take that as the exponent part. Since this logic is effectively the same, we continue to do everything we've done before, but with a small caveat. As I mentioned earlier, thinking of power as something that we're able to divide by shifting the decimal point left or right will help us over here in this section. So in the earlier implementation, if we scroll just a little bit to the top over here again, we multiplied power by 10, and then we divided it by in the end. Going back to your standard algebra math, multiplying by 1 over something versus dividing by that same thing gives you the same result. Hence, here what we're going to do, we're going to divide the value, we're going to divide the power, which is going to then enable us to multiply by this resulting power in the end. We'll see that in just a few moments. Again, if we encounter the exponent part after the decimal point, logic is the same as before, and there's a comment here which you'll be able to read in more depth in the GitHub repo. You'll be able to see that we do the same parsing as before. We pull out the exponent part and we handle it. Now, one of the interesting things we have to do is we actually have to take care of the exponent sign over here. And we have to flip it. The reason being is that because we're going to have to run with a for loop. And the for loop that we're going to be looking at is going to have to multiply the power over and over again, or divide the power by 10. Since the for loop runs from 0 until the exponent part, i.e. that many iterations, we need to have a definitive end. If the exponent sign was negative, we really are going to find ourselves in a little bit of a tricky situation. So this helps us solve the negative part, and therefore we essentially just keep track of it and say, hey, if there was an exponent sign, then we're going to handle it, and we'll see in a second what we do with it. And if there wasn't a negative part, then we're just going to do the multiplication. This is where it comes into place here, is that we're able to continue to have the exponent part be our limit, because we've made sure it's always positive as a result of this calculation up here. But we're making a decision based on the exponent sign whether we are multiplying or dividing our power. And finally, as we get to the end, we, instead of doing a multiplication and then a division, we're able to multiply the sign that we computed from the original value times the value that we parsed out, and then shifted by the power. And in this instance, we're either multiplying by 1 over or by the number of decimal points that we needed to do. I mentioned earlier that we added another method. It's called parse int at index. Since this is entirely a section of the book that's dealing with the idea of functions, it's a great opportunity to create our own function. Now, I'll take a small caveat that in production systems and in code that I would be writing in production, I wouldn't take this approach. This is not an ideal function and how it should be implemented. We will deal with it in later chapters as to why that is the case. But for the sake of this example, it is good enough. What we receive here is the string and the index into that string where we're going to start parsing. And this method here is very similar to what we saw above, but the only thing it handles are values that are integer-like. Effectively, it helps us to parse out the integer value as opposed to anything that might be with a decimal point. But since there's no decimal point for an exponent part, therefore we don't need to worry about that parsing. So this is going to be available in the GitHub. You'll be able to see that in the repo. Ask questions or leave comments, and I'll be happy to dive into that as well and explain it further if anyone has any. Now, for the sake of completeness, we wouldn't be able to claim that we've solved the problem without actually demonstrating it working. So let's go ahead and run the program. And I'm going to enter some values. Let's start with, let's say, just 23. We'll see that 23 comes into place, so that works. Let's go ahead and add 14.56, so we get something that looks quite right. Maybe do a subtraction of minus 55.98. And now, so we've seen that all of those cases work. Let's go ahead and add the exponent part. So let's start with the basic case of 5e2, so that should add 500. Yep, that looks like it did that. What about if we do negative 32.56e, and let's do a negative over here as well. Let's say negative 1, and just shifted by 1 decimal point. Yeah, looks like it did that as well correctly. What if we did just a negative 0.2345 e, and then we're going to shift the decimal to the right that many points. So let's go ahead and do 4. Let's see what we get. Yeah, it looks like we got the right thing because it was a negative value and we shifted it correctly. So that all looks like it's working. So this should convince us well enough that things are right, but let's just do one more. And let's do ahead and do 215.32 e, let's say e negative 2. Yeah, looks like it's all doing the right thing, and we can add more of the values, but it gets a little tricky to represent it the moment you go beyond really single-digit exponents because of just how much the whole thing moves. As a quick concluding thought for this presentation, what we've observed earlier is something known as Backus-Naur Form, or Backus-Naur presentation of being able to parse numbers. So a floating point number in Backus-Naur form is defined as having an optional sign followed by some number of digits, and then a decimal point, and then some number of digits. The star means that there's 0 or more digits there. Or another way of reading it is that you have a sign followed by at least one digit, because if you have one digit, you don't really need a decimal point in this instance. You can do something else. And you can parse it along this way. In this instance, if you have it, then the exponent part comes right over here. This is the e part. On the other hand, your e part can also happen here, or it can also happen in here as well. And so being able to articulate it, I'd be able to articulate that this is where your exponent parts comes in, and this also can happen right here as well. Be able to articulate that your exponent parts go over there significantly simplifies how we reason and think about the parsing logic. This is known as BNF. And I'm going to put the link down in the description. And Backus-Naur form is sort of a standard way of being able to parse different kinds of strings and different kinds of programs. A floating point is just a part of a broader program, but we can define it in a very set way that makes parsing fairly trivial and almost elementary in understanding.